Welcome to this hands-on tutorial on CNTK. My name is Amit Agarwal, and I'd be presenting this tutorial together with my colleague Frank Seide from Microsoft Research. So here is an outline of the tutorial. We will begin by taking a quick look at the setup requirements for the hands-on lab sessions in this tutorial. That will be followed by an introductory talk to give you an overview of CNTK. Following that, we'll have our first hands-on lab session where you would set up CNTK on your machine and get started with using CNTK. Thereafter, Frank will give a quick introduction to BrainScript, which is CNTK's custom scripting language for defining arbitrary neural networks. Then we'll have our second hands-on lab session where you would learn to define and train a recurrent neural network for a text language understanding task. Then we'll have a quick preview of the upcoming Python, C++, and .NET APIs for CNTK. And finally, time permitting, we will have our final hands-on lab session where you would implement image recognition task using convolution neural networks. So these are the setup instructions to prepare your machine for the hands-on lab sessions in this tutorial. You would find a link to this page from the KDD page for this tutorial. The downloads required here are pretty large. I don't know how much luck you are having with the downloads. If you're having issues, we have prepared about 20 USB sticks that already contain all the required downloads on them. So feel free to grab one of these and copy the files locally. Also, if some of you are having trouble looking at the slides from the back, the slides are available online, so you can download them and follow along. Yes. Yes. If you don't mind, could you please return the USB sticks once you are done? As we promised, we'll return them to the organizers. We kind of scrambled to get them at the last minute. By show of hands, how many of you are running Mac OS on the machine that you plan to use for the tutorial? Okay, so about 7 or 8 people. CNTK is not officially supported on Mac yet. But what you can do is you can run a Docker container. You can run a Linux image inside a Docker container and just follow the Linux instructions inside the Docker container. Okay, so we will have, after the introductory talk, we will have a session where you can go through the actual setup instructions. For now, just please initiate the download so that by the time the introductory talk is done, you have the files locally ready to do the installation. Okay, so now I hand it over to Frank to start the introductory talk.
Yes. Where does the clicker go? Okay. All right, good morning. Welcome to the CNTK tutorial. Sorry, let me just change one thing here. Okay, so this tutorial, we would like to introduce you to CNTK, which is Microsoft's open source deep learning toolkit. My name is Frank Seide. I'm a principal researcher in Microsoft Research, and by training, a speech recognition scientist. And that's my colleague Amit Agarwal. I didn't pronounce your name very precisely. From the development team that actually does the development of CNTK, although we have a lot of contributors, including myself, from outside that group as well. But as you can see, this is a collaboration with many, many people. Deep learning, before we go into any technical things, I just want to give you a little bit of a background here. So deep learning in Microsoft is really exploding, as you can imagine. It's in every company. So we have products you might have heard about, the Cognitive Services API. There's Skype Translator. In Bing, there's a lot of users, including Cortana speech recognition, ads, relevance, multimedia. HoloLens is getting into it with image processing. And of course, there's a lot of work going on in research. So just for the fun of it, I would like to show you two examples of the cognitive services. So where's the web browser? So the first one is something called the caption bot. And the caption bot is a deep learning system where you upload a picture and it will describe. Sorry, we switched laptop in the last moment, and this laptop doesn't have a touchscreen. I don't know how to use this anymore. Okay, so where's the upload page? Do you see it? Oh, here. I think I need to reload the page. Upload a photo here. Yeah. Okay, so just 5 minutes ago, I took a photo in this room. And we're sending this now to an automatic captioning system, which is available at captionbot.ai. And let's see what it does. Well, it thinks it's a group of people sitting at a table with a laptop, and they seem so happy. I think that's about right. Then the other cognitive services that's also fun is, maybe you heard about that in the press in the past, is howold.net. You upload a photo, and what it will do is it will try to guess how old the faces are in the picture. I'm going to load the same photo, and it finds Anton, my colleague in the middle, is covered, unfortunately, is 32. Is that about right? Okay. Okay, good. So let me continue with the presentation then. So the other thing that deep learning really made a big difference was in speech recognition. So this is sort of the area that I come from. Here you see plots of speech recognition error rates, how they did come down over time. And a very interesting curve for me is this red curve here, which is about transcribing conversations between people. For example, what you would need to do, for example, build an automated Skype service like the Skype translator. And you see that it kind of plateaued at some point at about 24% word error rate. And then in 2011, when we introduced deep learning into the mix, it came down to 16 from 24. So it was in total, actually a little bit further, it came down to 14. So it was something like a 40% cut of error rate just by introducing one single new technique, and that was deep learning in one specific aspect. And by now we're at around 8 to 9 with this. That's getting very close to human accuracy already. And just as a last little introduction, I want to give you an example on what does it look like when you're at something like 8 or 9% error rate. So this is a demo we gave, I think 3 to 4 years ago in China about translating a speech. And initially what you will see is, this is our corporate vice president of research at that time, you will see his speech being live closed captioned by a speech recognition system. Oops, where's the link?
In just the last few years,
Read along.
the combination of statistical techniques and big data have allowed us to do a much better job than we previously were able to do in being able to translate web pages or other kinds of information into other languages.
Okay, so you see it's actually pretty readable, right? And this is something that maybe before deep learning entered the picture was completely unimaginable. You can even take it one step further. You can now combine that with a translation system. And this is going to be the last demo I'm going to show you. Just have a look. Whoops.
So this technology is very promising. 用这个技术很有希望。And we hope in a few years that we'll be able to break down the language barriers between people. 数年后，我们希望能够打破人们之间的语言障碍。Personally, I believe this is going to lead to a better world. 这我个人认为这将导致更好的世界。I hope you enjoy the rest of the presentations today.
Yes, I hope you do. So this gives you an idea on what you can do with deep learning, what deep learning has enabled for us. And lastly, there was also a revolution on the image recognition side. So compared to 2010, the error rate of ImageNet recognition came down from 28% to 3.5%. This is the system that was done by our colleagues in Microsoft Research in China using the residual net technique. Okay, so what I would like to do today is, first I want to give an idea on what is CNTK, what are the key aspects of it, and so on. The second is, how do you use CNTK on a high level? How would it fit into your workflow? What would it mean for you? And the third is, we're going to do a deep dive into two technologies that we have in CNTK that are a little bit special compared to the other toolkits. One is how we're dealing with variable length sequences, for example, for language processing. And the second is how we're dealing with parallelization of training. So what is CNTK? I have to put the clicker in. Okay. So what is CNTK? Well, CNTK stands for Computational Network Toolkit. It does not stand for CNTK is not a TensorFlow clone, or a Torch clone, or a Theano clone. I don't know why all the other toolkits begin with a T, so there's some serious innovation here from us. CNTK is Microsoft's open source cross-platform toolkit for learning and evaluating deep neural networks. CNTK expresses arbitrary neural networks by composing simple building blocks into complex computational networks, and we will see a lot of that later. And CNTK is production ready. It has state-of-the-art accuracies, is efficient, and very important, it scales to multi-GPU and multi-server configurations. So, Microsoft's open source cross-platform toolkit. We have used the open source model inside and outside the company. And you can imagine for a company of over 100,000 people, actually inside the company, it's also not like, the CEO says you all have to use CNTK now. This is still pretty much a bottom-up effort. And one thing that is important about this is that every development is open. Anything that even a developer inside Microsoft does is in some branch that is on GitHub. You can see all the partial stuff that I have worked on. You probably don't want to see it, but you could if you wanted to. This CNTK has been released in 2016 under a permissive license. The project started much earlier. It started about 4 years ago by my colleague Dong Yu from the speech group. And then it was released first on CodePlex with a somewhat more restrictive academia-only license. It is also used by more and more groups inside Microsoft, and all of the major groups have full-time employees that are contributing to CNTK by now. What's very important is that it runs on Linux and on Windows. And there are various wrappers going to be there very soon. For example, the .NET wrapper, Python, C++. We already support Docker, and we use CODNN4 at the moment. This is actually incorrect. This is coming soon. Okay, so now the most important thing about CNTK is this. We express arbitrary networks by complex computational networks. So what does that mean? So let's look at an example. I guess you're all familiar with this. So this is sort of the canonical deep network. It's deep because it has more than one hidden layer. And if you see what it does, well, it takes an input, multiplies it with a matrix, adds some bias, and runs it through a squashing function, in this case, a sigmoid. And that's the hidden state of this layer. That's the output. And this output is then the input to the next layer. Again, you multiply it with a matrix. You add a bias. You squash it. You get another hidden output. And this then is the input yet again to another layer, but the function here is different. It's the Softmax Classifier. And the Softmax Classifier gives you a posterior probability for each of the classes in your system. And if you want to train this, you also need to have a ground truth. Yeah, you need to say what you want to train it for. So you will provide labels, typically in one-hot form. And then you can, for example, use the cross-entropy training criterion, which is shown here in the formula. So let's first translate that into what that would look like in CNTK notation. Actually, it's pretty much exactly what you see there on the left. All right. Now, if we pass this to CNTK, it will do the following. It will convert this into a computational graph. So now you see each of those circles here, these nodes are operations. And these are basically inputs. So there's data inputs and there's sort of parameter inputs into the process. And if you follow this, you can see that it computes exactly what is shown on the right. And at the very top, you see this cost entropy criterion that's used for training. Okay, so this representation is also used by many of the other toolkits, so it's probably not too much new for many of you. So the nodes are functions, the edges are tensors. They're values that flow through the system. Other systems call it ND arrays. So they can be tensors of arbitrary rank. And what we also support is sparse tensors, sparse representations in many cases. The one important thing that this graph structure allows you to do is automatic differentiation. So automatic differentiation, what does that mean? Well, when we do the training, we run, say, a sample through the network from the input here to the output, and then we basically here compare how close is what we got to what we wanted to see. And then we sort of kick against the system a little bit to make it better the next time we try to run the same sample on it, right? And kicking against the system is basically adding the gradient of the objective function with respect to the corresponding model parameter, okay? And the nice thing is if you have these computational graphs, you can actually compute the gradients very easily. So for example, the gradient of the objective function with respect to this parameter here, W2, is just computed by the chain rule. It's equal to the gradient of this with respect to P, times the gradient of P with respect to this input, times the gradient of this input with respect to this, and so on and so on. So this allows the system to fully automatically compute the gradient, and all you need to provide, or we provide, is the individual gradient implementations of those nodes. Another thing that's very important is that CNTK uses deferred computation. So this whole graph is not something you would execute immediately, but rather you use this as a description and pass it on to an execution engine. And that allows some interesting things. For example, we can optimize. One important optimization is memory sharing. So for example, if you only want to compute, if you only want to do inference going from here to here without a gradient, you actually only need 2 memory buffers. Right? So essentially what you need to do is you have your input, you multiply it, and you write that into an output buffer. Now you add your bias, and where are you going to store the result? You can actually use the same buffer like here, that you used here, because you no longer need that one. And then you can go to this point when you compute this output, you no longer need this input. So CNTK has this method built in to analyze the structure of the graph and establish these sharing structures, and you do find that you can reduce, well in this case you can reduce it to only 2 buffers essentially. When you do training it's a bit more complicated because for some of those you still need to keep the original value to be able to compute the gradient. So for example, for the sigmoid, for this one, and I think for this one, you still need to keep a copy of the original input, but for the intermediate values, you still don't need them. You can compute the gradients without. So you still get something like a factor of 3 memory reduction, and that's kind of common. You get 2 to 3 times memory reduction if the full memory sharing is enabled. And lastly, what having a graph allows you to do is to edit the graph. So you can make modifications. For example, you can build a network layer by layer. So you train a network, and then you take some part out, you add another part to it, continue training, and so on. Okay, so it is this Lego-like composability that allows CNTK to support a very wide range of networks. And we have successfully run feed-forward DNNs, RNNs, convolutional networks. DSSM models are very important inside Microsoft, sequence-to-sequence models as well. Okay, and the last point I made on the slide is CNTK is production ready. The most important thing is that we want to use this, or we use this inside Microsoft for building real products. So we're not running on MNIST or some small corpora like that. For example, the Skype translator system that you saw in the beginning was trained on, 1.4 billion samples. So that's the kind of dimension that we're talking about. And CNTK is ready for this. That's very important. And one thing that it does is it allows to parallelize your training over multiple GPUs in a single box, but also across multiple machines with multiple GPUs through MPI. We're going to talk about that in much detail later. Okay, just a final comparison. So I feel a bit embarrassed. This is a comparison from December 2015. So these numbers are not really very accurate anymore today. TensorFlow, for example, has caught up quite a bit. So what you see is the blue bar is the specific feed-forward DNN that we ran this on. This is the number of samples per second that we can process. And you see that basically all the tools, in this case, so basically Theano and TensorFlow have caught up by now. So for the single GPU performance, it's about the same. Now the red bar shows you scaling to 4 GPUs in a single box. And there you can see that scaling of CNTK is nearly 4-fold here, whereas for Torch and for Caffe, we only reached about 2 times scaling. And then at that time, it was pretty much the only toolkit that allowed to run on more than one machine. So this green bar is using 4 machines of 2 GPUs each. And you see it still scales quite a bit. At some point, you will run into overheads and so on. OK, so that gives you the basic idea on what is CNTK. Next question is, so what does it look like to use CNTK? And how would it fit into the work that you are doing? So let's specifically talk about training, because that's the most involved part. So for training, the basic flow or the basic architecture is CNTK has 3 important components. It needs to know how to read your data. It needs to know what the structure of your network is. And you need to configure how to learn the model parameters, learning rates, and so on. And then you give it a corpus to run on, and it outputs a model, right? So what we need is configurations for all of this. So how do you do that? So CNTK is a little bit different from some of the other toolkits in that you are not running it out of a Python shell, for example, but it's a standalone executable. And the operation is going to be described by a configuration file. And so this is the command to run it. So CNTK config file equals, then you pass the path of your config file. And then you can give it, this is optional, you can give it the commands that you want to execute. And in this case, we have a command that's called train. And that links to another configuration block that has to have the same name. And that block internally says, OK, what action is this? So this selects an internal piece of code that is being executed, the train procedure. You also have to tell it which device you want to use, GPU or CPU, and which GPU. Or you can say auto, then it takes the best that it can find, or the next that it can find. And then you have these 3 sections here. This is the reader, the network definition. This is what we're going to spend most of the time with today, and the SGD parameters. So let's go through those 3. So the first is reader. Now, reader, why is that actually a big deal? If you run a simple set, for example, MNIST, you can just write a little Python script that just loads the corpus into memory, and that's it. But actually reading data is a pretty involved problem. What our experience in speech is that the data that we're running on were always just a little bit too big to fit into a single machine. So for example, when I did some of the earlier work, the corpus was 90 gigabytes, my machine was 64 gigabytes. Now the Skype translator set is 200 gigabytes, and my machine had 128 gigabytes. So the problem is, for stochastic gradient descent, you need to do randomization of your data. That means you need random access. But if it doesn't fit into RAM, you have a big problem. How do you do this? You need to page from the disk, and disks are very slow for random access. So CNTK has a special reader implementation that does that for you. So basically, it chunks your data into bigger chunks, and then only loads a randomly selected subset of those chunks into memory, and then pulls random samples from that subset. And in a way, it runs over with a rolling window over these chunks. So once in a while, a new chunk is paged in, another chunk is dropped out, and so on. And this is really, really, really involved when you get to I call them production workloads, right? And so CNTK has all of this built in. It also comes with stock readers for image processing, for speech, and we have a text format for general data. OK, so the next part is how do you specify the network, your neural network? Well, the neural network consists basically of a formula that tells you how do you get from your input to your output, computing your probability. You have to define what the inputs are, how that connects to your readers, and you have to define your training criteria. So now, when we describe these networks in CNTK, we call them brain scripts. So they're sort of a little bit silly. It's kind of the scripts according to which our little brain is operating. And so we have a custom little network description language, which we also call brain script. Now, that's not everybody's cup of tea. So in about a month from now, and Amit is working on that very hard, that we will actually provide a Python API and a C++ API if you prefer to do all of this from a Python shell. So let's look at brain script. Let's go back to our network. Well, so the first thing you can do is you can define variables. So for example, we're defining what the dimensions are. These are just scalar definitions that then can be used, for example, in these definitions of inputs. This is how you declare what the inputs are of the network. In this case, they're called X and Y. And you also declare parameters. So the parameters here are declared that this is the parameters that the system will learn for you. Okay, so we have W1, W2, down here. We also have the according biases. We have another W here. Okay, so you get the basic idea. This is a complete brain script that describes this little network that we looked at. It's actually very straightforward and very clear to read. There's only one thing that's a little bit tedious here, because here we have defined all the individual parameters one by one. Now imagine you want to build a residual net with 152 layers. You really don't want to have 152 of these parameter definitions here. So let's see if we can make this a bit easier. The first thing we can do is we can define functions. So in this case, we define a layer function, and this layer function then does all this definition here and computes the output. And you can also pass it a nonlinearity, and you would use it basically like this. All right? So that's already much better. It's already much more regular. But we can also do one step further. We can say, well, what if I want to make even the depth of the network a parameter? So now we can actually just use a recursive definition. So we define this function here, I call it DNN stack, for example, and we pass it in the number of layers. And then you can basically say, well, if the number of layers is 1, then it's just a layer as we defined it before. But if it's not, then what we do is we execute the layer function, but we pass it the output of a stack that has L-1 layers, right? This is very straightforward, actually. And then how will we use this? So here you can see that now we have a single line here, and the number of layers is a parameter. Okay, I think this is this. Yeah, so is there any question about this? Okay, so you can actually take this whole idea of functions one step further. So what we normally do is we go one step further in that we actually use function objects. So what does it mean to use a function object? Well, if you look at how we're using this now, I'm going to explain next what this is. So this says we have a dense layer of this particular output dimension and this activation function applied to this input. And you can define them, basically now you're using 3 of those. Let's look at how this is actually defined here. So the dense layer defines, like before, the parameters here. But then instead of directly computing the output, it creates another function that then is applied to the output. And then this is what it returns here. So this is basically just a record lookup here. Dot apply says just take this one and return this. And once we have this, then we can write our network in this form. And for example, if you have used tools like Keras or Chainer, then you will be familiar with this particular form. You can then also go one step further, and this is also something you might be familiar with from Keras, and I think Torch has that. You can write it in this way. So instead of invoking the individual functions, you can basically say, I create a sort of a meta function on top of that that just calls each of these functions in sequence, and then you just pass your input once. And that makes the network description now very, very simple, because now suddenly you directly represent the kind of structure that you have. You have this building block, this building block, this building block, and they're directly represented in the code here. And basically, let me see, you can even go one step further. You say, why even pass the sigmoid here? Why not just make it another building block here? Right? Okay, so this is what I wanted to tell you about BrainScript at this point in time. We're going to look at more detail later. Do you have any question here? Yeah.
Go back to one of the previous scripts where you had this apply bracket x in.
Yeah. Yeah.
So it's like the last line in your block here is the return value of your function, like in F# or something.
Yes. I mean, this curly bracket really defines a record, right? And saying dot something, it simply selects a field of that record. It has the effect of returning the element from that record. That's right. But only because it's this particular combination of a function.
So I could also say that I want to get the W element of this record.
You could, yes. Yeah, well, in this case, you can no longer, because we baked sort of the dot apply directly into the definition of the function. So this means the W and B are encapsulated. They're hidden away from you. You will no longer be able to access this. If you don't say dot apply there, then what gets returned is the entire record. But then you would have to say dot apply everywhere here, right? And that's kind of tedious. Okay. Okay, so CNTK BrainScript, yeah, it's a different language, but it's really, really straightforward. It has a very easily understandable syntax. It allows to define custom functions and these function objects for reusable modules. And it allows a high level of composability. And again, in the future, we will be able to, very soon, we'll be able to do the same things from Python and C++ and .NET. Okay, so where does the stupid name BrainScript come from? Well, so the idea is that, well, on one hand, it sort of perfectly expresses the grand ambition that we have with this, right, building a brain. But on the other hand, if you look at the two-letter acronym of it, it tells you where are we with respect to that today. Okay. And it makes for really interesting, check-in commits, and so on, edit more BS about this. And so on. So the last thing is we need to specify the learner. That's very straightforward. You have a couple of parameters you need to tell it. You need to tell it what is the mini-batch size, how many epochs, the learning rate, the momentum, and so on. Here I would like to mention one thing that's sometimes causing confusion. You see how I define the learning rate here. I said learning rate per sample. And that's actually very important. In CNTK, we specify these two parameters and pretty much all parameters in a way that is agnostic to the actual mini-batch size. So mini-batches are not considered averages over gradients. They're considered sums over gradients. And why is this important? It's very important because sometimes you want to increase your mini-batch size without actually affecting how samples get weighted in the process. Why would you want to do this? This becomes important when you do parallelization. In parallelization, you want to minimize the number of times you actually synchronize your values across multiple machines. And by defining everything in this way, it just takes a lot of cognitive load off you. You just say what your new mini-batch size is after some number of epochs, and you don't need to readjust all your parameters, which you would have to do in some of the other toolkits. Okay, so a typical workflow. What time is it? I think we're good. So typical workflow is, well, first you configure your reader, network, and learner, the way I just showed it. And then in order to train, all you do is you say CNTK, config file equals, and the path of your config file, and then you select the command you want to run. If you want to run multiple steps in one go, you can do that too. So for example, you can also define a section for measuring your test set accuracy. So this will actually execute both actions in one step, one after another. Now, if you want to parallelize, if you want to run this on multiple machines, all you need to do is this. You put MPI exec in front, and you say parallel train equals true. And you better make sure you say device ID equals auto, so it actually picks different GPUs for different processes. That's all you need to do. That works on single box, and it also works in a network with multiple machines if you have set up MPI exec accordingly. And it also works with wrappers. For example, Microsoft HPC is sitting on top of MPI exec, and there are equivalent things in systems in Linux as well. So once you have trained your model, you have more steps. So the first thing you can do is maybe you want to modify your model for some reason. Maybe you want to do a layer building process or something like that. So you can do this, and then you would end up with a command sequence like this, some first step of training, then you have some action that maybe adds a layer, and then you reference another training section, and so on. So this is how you control this. Now, if you want to apply the model, that's the next step, right? Once you have done it, so you can apply it in two ways. One is you can first apply it file to file in an offline fashion. And that can be done directly out of the CNTK executable, and there's just a different command that you have to define for that. And you can also directly evaluate CNTK models from C++ code and .NET code. And for that, we're providing a library called eval DLL. I don't know why it's also called DLL on Linux. I think that snuck in. And for the .NET version, it's called eval wrapper. Okay, so I think this gives you an idea on what the general sort of mode of operation is with CNTK, and we would now like to continue with a deep dive of two of the technologies, and I'll hand over to Amit for that.
Okay, so this part is a deep dive into some of the key advanced features in CNTK, specifically handling of recurrent neural networks and the techniques behind the scalability of CNTK's distributed training methods. So the base features of CNTK are similar to most popular neural network toolkits. Our core computation engine is capable of computing gradients for arbitrary neural networks using backpropagation and automatic differentiation. And the core training process uses stochastic gradient descent with common learning methods like momentum and AdaGrad for optimizing the model parameters. Besides these base features, CNTK also supports several high-level features for neural network training out of the box. So one of these useful features is by a simple config setting, you can enable automatic tuning of learning rate and mini-batch size through the training, instead of using a fixed value for these hyperparameters. The toolkit very aggressively shares memory across layers in the network, and it keeps the amount of memory consumed on the device during training to a minimum. And what this translates to is you can handle much larger models, and you can use much larger mini-batch sizes, which is very important for training efficiency. The parts that I'd be specifically covering in detail is the handling of recurrent neural networks in CNTK, and the main data parallel training techniques that are exclusively implemented by CNTK. So let's first look at recurrent neural networks. The way CNTK represents and implements recurrent neural networks is very different compared to most popular toolkits. So let's first understand how recurrent neural networks represented in CNTK. So we have our simple feed-forward network computation from earlier, and now we turn this into a recurrent network by first introducing a time variable, and this time variable indicates a specific time step in the sequence that you're currently processing. Now we turn this into a recurrent network by adding a dependency on the computed value at the previous time step. So now this function h1 here is a recurrent function because it not only depends on the input x at time step t, but also on its own output at time t minus 1. The corresponding CNTK implementation looks very similar, but there is one notable difference. There is no time variable t in this representation, right? So the notion of time in this representation is implicit. And the way the recurrence is being expressed here is using this magical node called a past value node, which is a way of accessing the value of a variable at a previous time step. So basically, the representation of recurrence here is symbolic, and there is no explicit notion of time in the graph. What this translates to on the computation graph is that the simple feed-forward network graph that we had earlier, it turns into a recurrent network via the addition of these cycle of nodes. And this cycle of nodes here represents a data dependence across time steps of the sequence being processed, right? So when such a graph is presented to CNTK, it applies the Tarzan's algorithm, which is basically a simple algorithm for finding the cycles in the graph. And now it identifies the nodes in the graph of being one of two types. So first we have the black nodes, and these nodes represent computations where there is no data dependence between the time steps of the sequence, right? Which means that these operations can be executed in parallel over all the time steps of the sequence. And the ones in red are the ones that have a data dependence and need to be executed time step by time step for the sequence. And this distinction is important because these black nodes, I mean, when you're targeting data parallel hardware like GPUs, it's extremely important that you present the maximum possible amount of parallelism to the hardware. And these black nodes allow you to do that. They allow you to execute all time steps in parallel, which maximizes the utilization of GPU hardware. And we end up only executing these small cycles sequentially, keeping the sequential execution to a minimum. So as I mentioned earlier, the way CNTK represents and handles recurrent neural networks is very different compared to most other toolkits, right? So if you were to take any other popular neural network toolkit, the way recurrence would be specified is not in the form of this loop in the graph, but by manually unrolling the steps of the recurrence for a fixed number of time steps. So when you construct the graph, you don't have a loop in the graph, but instead you actually have a very deep graph where you have unrolled the recurrence for a fixed number of steps. So the downside of doing that is now you end up with a model that is only capable of handling sequences of a specific length. It can't handle arbitrary length sequences because you already unrolled it for a fixed number of steps, right? So this is the key difference between manually unrolling the recurrence in the graph versus having a symbolic representation, because the resulting model from the CNTK representation can handle sequences of arbitrary length. The unrolling happens at runtime when you're actually processing the sequences. Another major issue that arises in training of recurrent networks is regarding training efficiency, right? So again, when you're targeting data parallel hardware, you want to present as much parallelism as possible to the hardware, which means you want to batch multiple sequences together and not process a sequence at a time. But in a typical sequence-based corpus, the lengths of the sequences are variable. Not all sequences are of the same length. And now you're trying to pack this data in a rectangular or in a regular tensor shape. But if the sequence lengths are variable, you would have gaps in this tensor, which contain garbage data, and they should not be used for computing the gradients, right? So this is something you typically have to deal with when you're training recurrent networks. This is where CNTK shines. It actually does this automatically on behalf of the user by taking care of the garbage values, and it actually does it very efficiently, as we'll shortly see, by packing the sequences in a way that the wasted compute cycles are minimized. So we try to make as much use of the compute cycles as possible, right? So let's understand this with an example where we compose a mini batch using multiple variable length sequences. So start with a long sequence, and we add this as one parallel processing stream. We find another sequence which is shorter. We add it as a second stream. Now the third sequence arrives, and we observe that this is short enough to be fit behind the second sequence. So instead of starting a new parallel stream here, we fit it behind the second stream. And in doing so, we are now effectively utilizing these available compute cycles, right, which would have gone wasted if we started a new parallel stream. So this is how we compose a mini batch by packing sequences in available gaps, and at the end we are left with this small amount of space where we can't fit anything, so this is essentially garbage. Now when you process this mini batch, there are two things that the computation engine takes care of for you automatically, right? So first, it keeps track of the fact that this is garbage, and these values do not contribute to the gradients, right? So when computing the gradients, this part is automatically masked out so that you don't get these garbage results into the computed gradients. The second part is the toolkit takes care of the fact that now inside a single parallel stream you have multiple sequences, and when we're executing these time steps one by one, and when we cross a sequence boundary, the toolkit automatically resets the initial state of the recurrence, right? So this is something you would not have to do if you arranged everything as separate parallel streams, but since we are doing this packing, this is something that has to be automatically handled by the tool. And the resulting speed up, because of this batching of multiple sequences together and this effective packing, you get nearly a 20x improvement in performance compared to a naive implementation that is just processing one sequence at a time. Just to summarize, CNTK's representation of neural networks allows you to create generic models that are capable of handling sequences of arbitrary lengths, and the training of recurrent neural networks using CNTK is both easy and efficient because of this automatic packing and batching of variable length sequences. So you don't have to do any bucketing, which is what you typically do in other toolkits, right? You would create multiple models, each one of which is capable of handling a sequence of specific length, and now you have to redirect it to the correct model based on what the sequence length is that you're trying to use. Okay, so the form of parallelism CNTK supports is data parallelism, which means if you are trying to train a model across multiple workers, you do so by having each of the workers have a copy of the model, and then between the workers, the training samples are divided, right? So each worker is working on a mutually exclusive subset of the training samples. And then each worker computes the gradients for the local subset that they're working on, and with some frequency, the gradients are communicated between the workers, right? So this is the general form of data parallelism, right? So there's nothing special going on here so far. From a scalability perspective, the key challenge is to minimize the communication cost. We need to make sure that we don't spend more time communicating than we do computing, because you can hide the communication cost behind the computation as long as it is smaller than the computation time on each worker. So let's look at a simple example, right? So if you had a very deep, large feed-forward deep neural network with 160 million parameters, and we were working with a mini batch size of 1024 samples, such that it takes 1/7 of a second to process these 1024 samples, and it takes 1/9 of a second to exchange gradients between two workers. Now this model, if we were to just naively exchange gradients, divide this between two workers and naively exchange gradients, it does not scale even up to two workers, right? Because if you divide this into two workers, Each worker now is only processing half of the samples, which is 512 samples. So it takes 1/14th of a second to do the compute, but your communication is 1/9 of a second. So your communication is dominating compute. And this does not scale even to just two workers. So there are two ways of tackling this issue of communication cost. One is you can communicate less amount of data, which is what the 1-bit SGD technique does. We'll see that in detail in a bit. And the second method is that you communicate less often, and this is what the automatic mini-batch size scaling and block momentum techniques do. And all of these three techniques are exclusive to CNTK, and these were developed at Microsoft. Okay, so let's first look at 1-bit SGD, right? The idea is, instead of communicating gradients at their full 32-bit fidelity, we quantize the gradients down to a single bit. We compress the gradients down to a single bit and only communicate 1 bit for every gradient, right? Now, the downside of this is that if you compress it so aggressively, you would have a huge quantization error, right? The actual gradient value would be far different than the quantized value. And if you were to naively ignore the quantization error, the resulting, it'll have a very adverse effect on the training convergence. So the key idea in 1-bit SGD is, instead of ignoring the quantization error, we set it aside in the form of a residue and add it to the gradients for the next mini batch. And in doing so, what we are doing is, when we compute the gradients at the end of a mini batch, we don't communicate that gradient in its entirety in that mini batch itself, but instead distribute this mini batch gradient over time, right? So part of it will make it into the first mini batch, and the remaining parts will gradually make it over time by being part of the residue that keeps getting added every time we communicate gradients. And turns out we basically get a 32x compression effectively because of this, and empirically we find that it does not have any effect on training accuracy. So we were able to successfully scale up to 20 GPUs with no loss on training accuracy at all. So the next technique to reduce the communication cost is to communicate less often. And the idea here is to use larger mini-batch sizes, right? But if you were to just naively use larger mini-batch sizes, it affects the accuracy of the trained model. So the idea here is that this is something that the toolkit automatically does for you. You start small, and as the training progresses, the toolkit automatically scales up the mini-batch size to use larger and larger mini-batch sizes, but it takes care that it does not have any effect on the training convergence, right? So it scales up the mini-batch size as it goes on, and if it sees that that it's having an adverse effect on convergence, it rolls back to a previous mini-batch size. And what we empirically find that we start small with about 3,000 samples per mini-batch, and towards the later part of the training, the mini-batch sizes can go up to as high as 100,000 samples per mini-batch, which is now nearly 2 orders of magnitude reduction in communication cost. And this method can be combined with the previous method, so you can be communicating just 1 bit and using these very large mini-batch sizes towards the later part of the training. The final technique that I discuss is the most recent addition to CNTK's parallel training methods, and it is perhaps one of the most scalable techniques for data parallelism. So the idea here is to not communicate at the end of each mini batch, but have each parallel worker process a block of many mini batches. So at the end of each mini batch, each worker only updates the local parameters, but does not do any synchronization with other workers. And at this end of this block of mini batches, now we have this uber block gradient, which is the difference in parameter values from where we started to where we are now. We take these block gradients at each worker, and we aggregate them across all the workers. So this is now only after the block that we would be communicating with other workers. Now, if we were to take this large uber aggregated block gradient and apply it to the model parameters.
So in this block momentum, are you using the same data block each time or multiple times?
It's a fixed data block at each time. This is what we currently use. And as you see, these blocks are actually are super large. They're typically hundreds of thousands of samples. So there is really no need to try and scale the block size through the training. So now we have this uber block gradient aggregated across all workers. If we apply this gradient to the parameters, it's almost certain to diverge, right? It is too big of a step in the optimization process. So the idea in the block momentum technique is that we only apply a fraction of these aggregated block gradients, right? So if there are k parallel workers, we only apply 1/k of the gradients to the parameters, but we don't throw aside the rest, because if you throw away the rest, this is like model averaging, which is significantly slow in training. What we instead do, we take the remaining 1 minus 1 by kth of the block update and keep it aside in the form of a residue, very similar to the 1-bit HDD technique, right? And now we add this to the next block update that we get. So what we are effectively doing, similar to the 1-bit technique, we are taking these block gradients but not applying them in their entirety at one time, but gradually spreading their communication over time. And turns out this works very well, and it allows you to scale to very, very large block sizes, which dramatically reduces the amount of communication. Another way to think of this is very similar to the momentum formula, right? So what do we do in momentum? At each time we update the parameters by using a weighted average of the weighted combination of the current gradients and the smooth gradients that have been computed over the training history. So this is kind of a similar idea, which is where it gets the name momentum from, right? It's just happening across multiple workers on block gradients. So as I was saying earlier, empirically, this is perhaps one of the most scalable data parallel training techniques. We have observed speedups of up to 54x when training on 64 GPUs in parallel, which is very close to linear, and it's actually pretty impressive given that there is nearly no loss in training accuracy when you're using such massive levels of parallelism, right? And this has made a huge impact for our product groups, because now they can literally train production size models with tens of thousands of hours of speech data, or millions of images, or terabytes of text data in a matter of hours by using this parallelism at such a massive scale. So currently we are using 4 GPUs per node, so that is 16 nodes with 4 GPUs each.
How much RAM do you have on each node?
Each of the GPUs have 12 gigs of RAM.
And the whole data fits into memory of the...
It's only the model that needs to fit into memory, and because we use memory sharing, if you compare CNTK to most of the toolkit, you'd find the amount of memory consumed on the GPU is very low, because there are a lot of advanced compiler techniques that you can apply to a graph to reduce the amount of memory you compute. So, but the whole thing does not need to fit in memory. You basically take small mini batch sizes, and the entire state of that mini batch is what is the working set when you're processing. So
the whole CNTK runtime is scale up these mini batches and bringing them in processing?
right, so that happens in parallel, right? So you basically, each of the workers is reading a mini batch, it's prefetching those mini batches, and the computation is happening on the GPU. So there is kind of a pipelining of reading and computation going on, and this is happening in parallel across all these 64 workers. Okay, so to conclude, CNTK is Microsoft's open source cross-platform toolkit for defining and learning arbitrary neural networks, and it allows unprecedented scaling compared to most other toolkits. The toolkit allows you to express arbitrary neural networks using basic building blocks. The toolkit is very efficient in training because of the use of techniques like the recurrent neural network techniques that I showed you earlier, and because of aggressive sharing of memory across blocks. Recurrent neural networks are both easy to define and are more general, and also very efficient because of this automatic batching of variable and sequences. The data parallelization techniques supported out of the box in CNTK are highly scalable, and CNTK is capable of handling inputs and tasks of a wide range of modalities like speech, text, and vision. So in short, CNTK is already handling production size models and production size data for various product groups in Microsoft, and it offers state-of-the-art accuracy, efficiency, and scaling across multiple servers. So this concludes the introduction part of the talk, and we will take a quick 2-minute break and then start our first hands-on lab session.